Hello everyone. Today we will learn about sampling distributions and the central limit theorem part 3. Previously we learned what's the central limit theorem, and today we were going to prove how the central limit theorem works, why this is true, and like that. Okay. Chapter 7.4 is about the proof of the central limit theorem. And before we prove the central limit theorem, let's state one theorem, which is theorem 7.5. Let y and y1 to y3 comma dot 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 be random variables with moment generating function mt and m1t, m2t, m3t respectively. So the random variable y have the moment generating function mt, and for random variable y1 it have moment generating function m1t, y2 is for m2t, and dot dot dot. And if limit n goes to infinity, mnt equals mt for all real t, if this is the case, then the distribution function of yn converges to the distribution function of y as n goes to infinity. So we know that this moment generating function uniquely describe the distribution function of the random variable. And if the moment generating function converges to some moment generating function as n goes to large, and then we can say that the random variable yn converges to random variable y. That's what the theorem means, and we will not going to mathematically prove this theorem. However, currently we will admit this theorem and just to use it. And if we are using this theorem to prove the central limit theorem, how can we use this? Yn converges to y. So we have sample mean of y bar, and what we want to prove is that y bar minus mu divided by sigma over square root of n. This follows normal distribution with mean zero, variance of 1 as n goes large. If n goes to infinity, then this one should follow normal distribution. This is what central limit theorem implies. And so what we want to do is that this y bar is actually yn bar. This yn, this is actually I equals 1 to n yi divided by n. So what we want to prove is that the m and t, the moment generating function of the yn bar, that goes to the moment generating function of standardized normal distribution, and then that would be the proof for the central limit theorem. That's how we prove the central limit theorem. Let's try to go details. Suppose y1, y2, and yn is a random sample from any distribution with mean mu and variance sigma squared. Then the central limit theorem is that y bar minus mu divided by sigma over square root of n goes to the normal distribution, standardized normal distribution, as n goes large. This is the central limit theorem, and so let's define un as this quantity, and if you specify this y bar is sum of yi divided by n, and if you put y bar this thing divide n, and if you multiply n each side, you can check this one is same as this one, and also if you put this n mu inside of the sigma and put sigma inside of that sigma, you will find that this one is also the same as un. And now let's define each of yi minus mu divided by sigma as zi, and you can find that zi, expected value of zi, is expected value of y minus mu, which is 0, and variance of zi is 1, sigma square divided by sigma square, which is 1. And then what you know is that the moment generating function of the sum of zi's, which is mz1t, mz2t, dot dot dot, and since all zi's are independent random sample from the same distribution, we can specify this as mz1t nth. Okay. And from here, un is sum of zi's divided by square root of n from the previous equation. And so m sum of zi t is expected value of e to the minus zi t, and the moment generating function for un t is e to the expected value of e to the minus square root of zn divided by square root of n t. And so this is actually m square root of zi. If we put this together, then it's t over square root of n. And so we can see that munt is actually this one, and this one is, since zi's are independent, mz1 t over square root of n to nth. Okay. And by Taylor expansion, we can do Taylor expansion on mz1t at a equals 0, at a equals 0, and that's the mz10 plus mz1, the one derivative, first derivative, and put 0, and t minus 0 divided by 1 factorial plus, and at some point we stop, and we put psi inside of the here, and then they are equal by using Taylor's theorem. And in here we can write this part using big O notation. So in here, z1 0, which is expected value of e to z1t, it's 0. So that's expected value of 1. Expected value of 1, which is 1. And what about z1 first derivative of this? And this is e to the expected value of the z, and this is 0. And what about mz 2 derivative of 0, which is expected value of z square, which is actually variance of z is expected value of z square minus ez square, which is 1 minus 0, so ez square is 1. And so we can put these values. mz1 0, this is 1, this is 0, this is 1, and so we have this thing for this part. And for here, this is constant, and 3 factorial is also constant, and this part is t third, and so we can use big O notation to simplify the notation. What this means is that the speed of convergence of this term is same as t third. Uh, uh, okay, and uh, we can put we want to calculate the moment generating function of u and t, and which is this one, and in here we are putting t over square root of or n, and so the u and t can be written as this one, 1 plus t square over 2n plus big O t third over n square root of n and n. Okay, and what we want to do is we want to do limiting distribution of this term. We want to limit n goes to infinity, and we want to check the distribution. What would be the formula here when n goes to large? So we want to check the limiting number. We want to check as n goes to infinity, what would be the limiting value of this thing. And and here, if you admit that this part goes very small, this part goes very small as n goes to infinity, this part approaches to 0 so much faster than this part. And so if you think like that, then limit n goes to infinity, it's 1 plus t squared over 2n to n, and this thing is actually limit n goes to infinity, 1 plus 1 over 2n over t squared, and 2n over t squared times 2 over t squared. And actually, you know this limit n goes to infinity, 1 plus n over 1 n, and this is e. You know this from the calculus. And so as n goes to infinity, uh, actually this thing goes to infinity. Actually, we can put 2n over t squared goes to infinity, and let's put 2n over t equals k, and then this one is actually limit k goes to infinity, 1 plus k, 1 over k to the k, and here 2 t squared. And so this is e to the t squared over 2. Okay, so this one converges to e to the t squared over 2. And actually, this is the moment generating function for standard normal distribution. And so this is MGF for the standard normal distribution. So we prove that UN converges to standard normal distribution as n goes to infinity. That's the proof for the CRT. Actually, probably there should be someone that this part may not make sense. Actually, in this proof, actually I didn't mathematically rigorously prove that why this O t third n square root n part, why this part is negligible. I actually skipped this part, and so I will give you another statement that to prove this part. Okay, I will move on. Okay, so actually there's the other way to solve this limiting value. Um, and let's say if the answer for this limiting value is a, and you can take log of the both sides, and so limit n goes to infinity, and log of this thing is n times 1 plus t square over 2n plus o n square root of n t third equals log of a. And now as n goes to infinity, this n part goes to infinity, and this part it's actually log of this thing. N times log of this thing. So this n part goes to infinity, and this log of this thing part here, this part goes 0, this part goes as n goes to infinity, this part also goes to 0, and so this part converges to log 1, so this part goes to 0. So this is infinite times 0, and so it's hard to get the limit value. However, we specify this n as 1 over n, and so if we write this thing as limit goes to infinity, log of 1 plus t square 2n plus o t third n square root of n and 1 over n. And now this part goes to 0 as n goes to infinity, and the upper part also goes to 0. So now we can apply the L'Hopital's rule. So this looks like 0 by 0, and so we can apply L'Hopital's rule for numerator and denominator. And so if we apply the L'Hopital's rule, let's get the derivative of 1 over n, which is n minus 1, and so this is minus n minus 2 square. And what about the upper part? Log of x is 1 over x if we derive with respect to x. So 1 plus t square divided by 2n plus o t third n square root of n divided by we get derivative of the inside part here, which is well, and we derivative respect to n, so t square over 2 minus n negative 2 and plus the other part is actually this part is ot square t third times n negative 5 over 2. Okay, so this one is this thing, and from here as n goes to infinity, and actually this n second part we can multiply numerator and denominator n square multiply n square both sides, then this part cancel, this part also cancels, so so the result is that minus 1 plus 2 n t square plus o t third divided by n square root of n, and upper part is minus 2 t square over t plus o t third n minus 1 over 2. Okay, now as n goes to infinity, now as n goes to infinity, this part goes to 0, and this part goes to 0, this part goes to 0. So the limiting value would be minus t squared over 2 divided by minus 1, which is t squared divided by 2. So what we proved is that log of a is equal to t squared divided by 2. And so a is e to the t squared divided by 2. So this is exactly same as what we proved in the last slide, but with slight different trick. And so so we can say that this a is e to the t squared divided by 2, and actually this is MGF, moment generating function, for standard normal distribution, normal 0, 1. Okay, so this is the proof for the central limit theorem. Chapter 7.5 is about the normal approximation to the binomial distribution. This is one example case where the central limit theorem can be used. So you can think of this as one example that central limit theorem is used in the certain situation. And here, in this situation, CLT, central limit theorem, can be used to approximate probabilities when the exact probabilities are tedious to calculate. So if something follows the binomial distribution, and if n is very large, then we know that certain random variable, let's say x, follows binomial distribution np, and if n is very large, and sometimes calculating the probability of related to x, like certain quantity, even if we know the exact distribution, that binomial distribution, the calculating the exact distribution, sometimes it's very time consuming, and in that case we can apply the central limit theorem to calculate to approximately calculate the probability. Okay, let's check how it can be used. Suppose y has a binomial distribution with n trials and probability of success p, and we can think of this binomial distribution as sum of Bernoulli trials. Actually, we already learned this a little bit in the discrete random variable case. You can check that part as well. We can think of n number of Bernoulli trials xi's with success probability p, and the y follows binomial distribution. So y follows binom np, and xi's are Bernoulli trial with p, and you can check that this binomial trial is actually sum of Bernoulli trials, and from here you can see that the y over n, which is can be thought as sample mean for independent Bernoulli trials, and ex bar, which is y over n, that's expected value of x bar is p, and variance of x bar is p times 1 minus p over n. And well, the reason is because expected value of Bernoulli trial is p, variance of Bernoulli trial is p 1 minus p, pq, and so from here you can derive these. Okay, and by applying the central limit theorem as n goes large, you can check this thing. And another word, x bar minus p divided by p1 minus p over square root of this thing, square root of p 1 minus p over n. This follows normal 0, 1. Okay. To check the usefulness of the normal approximation, let's look at this example first. Example 7.10. Candidate A believes that she can win a city election if she can earn at least 55% of the votes in precinct 1. She also believes that about 50% of the city's voters favor her if n equals 100 voters show up to vote at precinct 1. What is the probability that candidate A will receive at least 55% of their votes? Okay, so we have 100 voters, and each voter follows Bernoulli trial. Bernoulli trial with P, and so and Y is the sum of xi's, which follows binomial distribution with NP, and we want to check the probability that candidate A will receive at least 55% of their votes, and the estimate of the vote rate would be Y over N, and we want to calculate the probability of Y over N is greater than or equal to 55%. So we want to calculate this thing, and here she believes that about 50% of the city's voter favor her. So the P here would be 0.5. That's her belief, and we want to calculate the probability on assuming that what she believes, this thing. And so by using normal approximation, we can calculate this one. Y over N minus P 0.5 divided by square root of 0.5 times 0.5 divided by square root of n, which is 10. And so this is greater than or equal to 0.55 minus 0.5 divided by square root of 0.5 times 0.5 divided by 10. Actually, it's 100. So the variance of Y, expected value of Y bar is 0.5. Variance of Y bar is 0.5 times 0.5 divided by 100. Okay. mm, yeah. So mm, you can calculate this value, and as n goes to large, this n equals 100 is large enough value, so we can assume that this follows standard normal. So you can calculate z is some value of this thing. So you can approximate this value using the standardized normal distribution and by using CLT. And actually calculating this way, it's a lot easier than directly using binomial distribution. If you want to use the binomial distribution, I think you should calculate the probability of among these 100 voters. You have to calculate when um, y equals 1 or y equals 0 to, so you should derive the distribution for y. Y equals 0 to y equals 100, and you can calculate probability of these things, and you sum up these probabilities to calculate this one. So to calculate this one, if you use binomial distribution, probability of y is greater than or equal to 55. So you should calculate probability of y equals 1 to 55. Okay. Next topic is when can we approximate normal on binomial distribution? So we stated that binomial distribution goes to normal distribution as n goes large. Then when can we approximate normal on binomial? How large would n be, like that? So and also in the previous lecture, when we were learning about discrete random variable, uh, I said that binomial NP follows Poisson distribution as n goes large. Why binomial converges to normal this time? Something like that. And actually, in this situation, we were dividing the certain interval with n number of subintervals. So in this case, when the situation binomial converges to Poisson distribution, the situation is like um, lambda equals np. There's restriction of lambda equals np. So, and we are dividing this interval with n number of subintervals. The p goes to 0. So if n goes to infinity, p goes to 0, and lambda is fixed constant. In this situation, binomial distribution converges to Poisson distribution. And however, if the p is fixed constant and n goes large, in this situation, binomial distribution converges to normal distribution. Okay, and in the textbook, the suggested criterion is something like this. If n is larger than this quantity, then probably we can approximate binomial with normal distribution. So if p is 0.3, then larger of p and q, which is 0.7, so 0.7, smaller of p and q is 0.3 times 9. And so we pick, if n is larger than this quantity, then it would be okay to approximate the binomial distribution with normal distribution. That's suggestion from the textbook. And figure 7.8 describes the example of normal approximation and the binomial distribution when n equals 10 and p equals 0.5. These histograms, rectangular, these rectangles are probabilities for the binomial distribution. So, um, so in this case, p probability of um, y is less than or equal to 1 can be approximated probability of w, which is corresponding normal distribution of this continuous thing. So the y is less than or equal to 1 is sum of these two rectangles, and that quantity can be approximated by the region of this red area, which is w is less than or equal to 1.5. Okay, so like this way, you can approximate the binomial distribution with normal distribution. Okay, let's move on to example 7.11. Suppose that y has a binomial distribution with n equals 25 and p equals 0.4, and find the exact probabilities that y is less than or equal to 8 and y is equal to 8, and compare these to corresponding values found by using the normal approximation. Okay, so the y follows binomial distribution. N equals 25, P equals 0.4. This is the distribution for Y. And what about corresponding distribution W? That is normal distribution. And this binomial distribution converges to normal with NP 25 times 0.4, and the variance is NPQ. So 25 times 0.4 times 0.6. That's the corresponding normal distribution. Okay, and to calculate probabilities that of this thing, we can use the binomial table in the appendix. So you can solve that probability of y is less than or equal to 8. You can calculate this quantity is 0.274 using the table in the appendix, and also you can calculate, you can approximate the probability of this thing using the normal distribution W with this solution, and compare the results, and the results very similar, 0.27, and difference comes from the third digit, and okay, and let's move on to calculating probability of y equals 8. You can calculate the probability of y equals 8 using binomial distribution, using this quantity and that quantity. Probability of y is less than or equal to 8, and probability of y is less than or equal to 7. If you subtract these two quantities, you can get the probability of y is equal to 8. And to calculate the corresponding normal approximation, that you can calculate the probability of W is from 7.5 to 8.5. And actually you can check this figure here to calculate probability of y equals 8, which is this thing, and you can approximate it using a normal distribution from 7.5 to 8.5. And so the rectangular area is approximated from this red area. Okay, And you can calculate this probability using normal distribution. You normalize this W with corresponding standardized normal distribution, and then calculate it using the normal table. Okay, let's move on to one exercise problem, which is exercise 7.82. The quality of computer disks is measured by the number of missing pulses. Brand X is such that 80% of the disks have no missing pulses. If 100 disks of brand X are inspected, what is the probability that 15 or more containing missing pulses? Okay, so probability for missing pulses, no missing pulses is 80%. So the Y follows binomial distribution with n equals 100, 100, and p is probability for missing pulses. Then 80% of no missing pulses implies that probability for missing pulses is 0.2. Okay, and we want to calculate the probability of y is greater than or equal to 15. 15 or okay, so you want to calculate this thing, and what's the corresponding normal distribution? So y follows binomial listing, and the corresponding normal w would follow normal distribution with mean is np. Np is 100 times 100 times 0.2, and the variance is NPQ, 100 times 0.2 times 0.8. So this is the corresponding normal distribution, and we can approximate this probability with W is greater than or equal to 15.5, and this is probability of W minus NP, 100 times 0.2 divide by square root of 100 times 0.2 times 0.8 is greater than or equal to 15.5 minus 100 times 0.2 divide by square root of 100 times 0.2 times 0.8. Okay, so this would follow the standardized normal distribution Z, and if you calculate this value and calculate this thing from the table, then you will get the answer for this exercise question. Okay. And here is the homework for chapter 7.5. Okay, thank you very much for your participation through this whole semester of the course. And I also enjoyed a lot teaching this Mathematical Statistics 1 class, and I hope everyone also enjoyed it. And good luck on the final exam, and I hope to see you in class in the next semester. Everyone stay healthy and have a great summer break. And thank you and see you.